Okay, we're going to start the random variable notes. So first, let's look at a probability model. A probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. So a random variable takes on numerical values that describe the outcomes of some chance process. Probability distribution of a random variable gives its possible values and their probabilities. Okay, so probability distribution is basically a table of probabilities. So let's look at an example. Consider tossing a fair coin 3 times. Define X as the number of heads obtained. So let's look at our options. Okay, if I toss a coin 3 times, I have options of either heads or tails. So I could get 3 tails, a head, 2 tails, tails, head, tails, etc. So our options are there below. So a probability distribution is just creating a table. So what I could have 0 heads, how many times? Just 1 out of 8, because that's if I get all 3 tails. I could have 1 head. How many have 1 head? That would be 3 out of the 8 possibilities. I could get 2 heads, 3 out of the 8 possibilities. And all 3 heads, 1 out of 8. So probability distribution, think about it as a probability table. We can also graph a probability distribution using a histogram. Notice this one is approximately symmetrical. So there are 2 main types of random variables. We call them discrete and continuous, just like when we talked about data in a previous chapter. Let's start with discrete. Discrete takes a fixed set of possible values with gaps between. So think about counting, okay? When we count, we don't include all the itty bitty decimals in between, okay? You count by 1, 2, 3, so forth, okay? So discrete means do not include all the itty bitty decimals in between. And with discrete data, again, as always, every probability is a number between 0 and 1. The sum of all your probabilities in your distribution need to add to 1. And to find the probability of an event, add the probabilities of the particular values that make up the event. So discrete random variables commonly arise from situations that involve counting something. So situations that involve measuring something often result in a continuous random variable. So continuous random variables takes on all the itty bitty decimals in between. So it's all the values in an interval of numbers, including all the decimals in between. Probability distribution of X is described by a density curve because those are typically normal curves. So when we find those probabilities under the normal curve, that would be continuous random variables. The probability of any event in the area under the density curve and above the values of X that make up the event. So the probability model of a discrete random variable X assigns a probability between 0 and 1 to each possible value of X. The continuous random variable Y has infinitely many possible values, again, because it includes all the itty bitty decimals in between. All continuous probability models assign probability 0 to every individual outcome. So you're not going to be able to make a table, a probability distribution table with continuous random, okay, because you have infinite possibilities. But only intervals of values have positive probability, so only intervals. When analyzing discrete random variables, we'll follow the same strategy we used with quantitative data. You're going to describe the shape, center, spread, and outliers. So think about your socks. So how do we find the mean? So when we're talking about discrete probability tables, the mean here called the expected value can be found by this equation. So you're going to take the value and multiply it times the probability plus the second value times the second probability plus so forth. Okay, so expected mean, make that a vocab word, means expected value is equal to mean in regards to probability table, and expected value is the summation of your value X times the probability, add them all together. So let's look at an example. So if we consider APGAR scores, what's typical? So again, APGAR score is a score that doctors give babies when they are born, just tell how healthy they are. So they get a score from 0 to 10 based on a set number of criteria. So compute the mean of the random variable x and interpret it in context. So expected value, if we're looking for mean, again, we're looking for expected value. That means sum up all the x times the pi. And again, you do have to do this by hand. There's no magic button you can click on the calculator for. So you do have to hand calculate this, unfortunately. But multiply each value, 0 times 0.001 plus 1 times 0.006 plus 2 times 0.07 and so forth. All of that added together is 8.128. So on average, because again, expected value is mean, on average, when babies are born, the APGAR score is 8.128. Okay, so again, how do you interpret that in a sentence? The mean APGAR score of a randomly selected newborn is 8.128. And again, this is the long-term average, not just that, oh, the probability that the next baby is going to have that score. So if I do this over and over again, repeatedly. Note the expected value does not need to be a possible value of x or an integer. Okay, it is a long-term average. So notice the average can be a decimal, but your values will not be in any discrete probability table. And again, always think logically, okay, your average should be about in between your data values, depending on, if probability is higher on the top or the bottom. So stats is all logic, so make sure to check your answer for reasonableness. So joke, maybe it's funny, maybe it's not. The best way to make this decision is by calculating the expected value of each possible outcome. You multiply the must pretend to be dead. I sense that we're done here. I hope the dead sometimes cover their ears. So maybe it's funny, maybe it's not. Since we use the mean as the measure of center for a discrete random variable, we'll use the standard deviation as our measure of spread. So the variance of a probability table, again, has this formula. And again, there's no magic button on the calculator. You have to hand calculate this. Luckily, this is on your AP formula sheet. So you can open up that AP formula sheet, make sure that you can find the variance, and the expected value equation is on there too. You just need to know what it means. So how we find the variance is we sum up each x value times the mean. So you first got to find the expected value. So you're going to take the first value minus the mean, square it, times its probability, plus the second value minus the mean, squared times that probability, and so forth. Okay, so the value minus the mean squared times the probability, add those all up. And again, you must do that by hand. There's no magic button on the calculator for that, but it is on your formula sheet. Find it there. And standard deviation is just the square root of the variance. So you can square root the final answer to find the standard deviation. Again, standard deviation describes spread on average, how far away is each data point from the mean. So compute the standard deviation of the random variable x and interpret it in context. Well, this is the same APGAR data. So we had already calculated the expected value to be 8.128. So we can just start with the first value, 0 minus 8.128 squared times the probability plus 1 minus the mean, 8.128 squared times probability, so forth. Do that for the entire data set. And you should get 2.006066. Again, that is a variance. So standard deviation, we're going to take the square root of it. So on average, a randomly selected baby's APGAR score will differ from the mean of 8.128 by about 1.4 units. So let's look at an example. If a player rolls 2 dice and gets a sum of 2 or 12, he wins $20. If he gets a 7, he wins 5. The cost to roll the dice 1 time is $3. Is this game fair? Okay, so a fair game means that on average you should either be able to get your $3 money back, or you make money, right? So a fair game is one where the cost to play equals the expected value. So let's draw out the probability model. What are the chances of winning 0? Well, if he gets a sum of 2 or 12, he wins $20. Well, how many options are there on 2 dice? Okay, and the only option to get a sum of 2 would be 1 and 1, right? We have a few more. We have option of we have an option of 6 plus 6 to get 12, right? So on a die, 6 times 6 would be 36. We get 2 out of 36, which simplifies to probability 1 out of 18. If he gets a 7, he wins 5. So again, this is a sum of 7. So that has a probability of 1 out of 6. Because we have a variety of options to get a 7, right? 1 and 6, we can do 2 and 5, we can do 4 and 3. Everything else, again, probability models have to sum to 1, so subtract from 1. So probability that he wins 0 would be 7 out of 9 after you simplify the fraction. So let's find the expected value here. If you find the expected value here, 0 times 7, 9, plus 5 times 1, 6, plus 20 times 1 over 18, we get a value on average, you get 1.944, which is less than it costs to play $3. So is this game fair? No, on average, I'm only going to get back $1.94. So the answer is no. So now we're going to move on to what's called the linear transformation rule. So we got a Pete's Jeep Tours. They offer a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run. And the vehicle will hold up to 6 passengers. Define X as the number of passengers on a randomly selected day. So we can create a histogram of the probability distribution here. And notice it is approximately symmetrical. So let's find the mean and the standard deviation. Again, mean is taking the X times the probability, add them all up, expected value. And if you do that, you should get 3.75. And standard deviation, again, is taking the X minus, so 2 minus 3.75 squared times 0.15, doing that all over again. For time's sake, we'll get 1.09. So if Pete charges 150 per passenger, the random variable C describes the amount Pete collects on a randomly selected day. So if there's 2 passengers at $1.50 each, he's making $300 with a probability of 0.15. Again, 3 passengers, 3 times 150 is 450 and so forth. So all we're doing is multiplying the number of passengers by 150. So here is our amount coming into Pete's Jeep Tours. Again, notice if we graph this probability distribution, it looks very, very similar, still approximately symmetrical. And again, if we find the expected value, 300 times 0.15 plus continual, we'll get 562.50. And again, if we use our standard deviation equation, we'll get 163.50. So what do we notice about our probability distributions? Notice they look pretty much the same, right? Approximately symmetrical. Approximately normal. Notice the center here is about 4. The center here is about 600, right? And if we take 4 times 150, we should get 600. Okay, so linear transformation rule says we can multiply, but it does not change the shape of our distribution. So what is the effect on a random variable when multiplying by a constant? So multiplying or dividing each value of a random variable by a number. Well, if you multiply, it divides, or divide, because again, division can be written as multiplication. It measures of center and location, so mean, median, quartiles, etc. by B. And multiplies measures of spread, so i.e. range or IQ or standard deviation, by the absolute value of B, because again, standard deviation can't be negative. But it does not change the shape of the distribution. So when we multiply by a constant, we can directly change that value by just multiplying, but it does not change the shape. We're just moving that distribution over. So think about in regards to algebra 2, when we have a translation, we're just shifting the entire graph over, but we're not making it steep or wide or so forth. And note, multiplying a random variable by a constant b multiplies the variance by b squared. So if we go back to PH Jeep Tours and we go back to our cost probability distribution, and remember we calculated the mean and standard deviation as such. So this is how much money Pete is bringing in, okay? But it cost Pete $100 per trip in order to buy the permits, the gas, and the ferry pass. Random variable describes the profit Pete makes on a randomly selected day. So he makes 200 profit with a probability of 0.15, 350, so forth. So profit is actually take-home pay, right? How much brings in minus how much it actually cost. And if we graph that probability distribution in a histogram, so again, what do we notice? If we look at the graphs, again, both of them are approximately normal. But what do we notice about the means? Here we have a mean of 462.50 and a standard deviation of 163. What changed? What did not change? Notice our standard deviation did not change. It stayed the same. Which is why our graphs look the same, right? Or similar. So when adding or subtracting a constant, because there again, the cost was making a profit of 100, adding the same number, a, which could be negative to each value of a random variable, adds a to measures of center and location, does not change measures of spread, range, IQR, standard deviation. It does not change the shape of the distribution. So think back to our linear transformation rule that we did with earlier in the year. Same rule still applies. If we're multiplying by something, mean and standard deviation will change. If we add or subtract, mean will change, but not the standard deviation. So whether we are dealing with data or random variables, the effects of a linear transformation are the same. So if we put it in our linear equation, if y equals a plus bx is a linear transformation of the random variable x, then the probability distribution of y has the same shape as the probability distribution of x. And we can write it as this: mu sub y equals a plus b mu sub x, average of x. The standard deviation of y would be absolute value of b times the standard deviation of x. But again, standard deviation can never be negative, so which is why we have to add absolute value. So far we have looked at settings that involve a single random variable. Many interesting statistics problems require us to determine 2 or more random variables. So let's investigate the result of adding and subtracting random variables. Let x equal the number of passengers on a randomly selected trip with PH Jeep Tours, and let y equal the number of passengers on a randomly selected trip with Aaron's Adventures. So let's define the total of x plus y, and what are their means and their variance. So we go back to our probability distribution of passengers, typical numbers of passengers with probability. We had already calculated previously the mean number of passengers is 3.75 and a standard deviation of on average difference as 1.090. So now we're comparing it with Aaron's Adventures. So Aaron's Adventure has a slightly different probability model. Probability of 2 is 0.3, so forth, and our average there is 3.10, and our standard deviation is 0.943. So what do we notice here? Do our distributions look the same? First one's definitely approximately normal. The second one, you might be able to say it too, it's slightly skewed right. But how many total passengers can Pete and Aaron expect on a randomly selected day? Well, since Pete expects mu sub x, 3.75, and Aaron expects mu sub y, 310, they will, on average, give a total of 3.75 plus 3.10, which gives us a total average of 6.85 passengers per trip. So the mean of the sum of the random variables, total equals x plus y. Then your expected value, again, we can directly just add. So total mean, just like previously when we did total mean, you can directly add your means. So in general, the mean of the sum of the several random variables is the sum of their means. So we can directly add our two sums together. So how much variability is there in the total number of passengers who go on Pete's and Aaron's tours on a randomly selected day? To determine this, we need to find the probability distribution of T. The only way to determine the probability for any value of T is if X and Y are independent random variables. Knowing whether any event involving X alone has occurred tells us nothing about the occurrence of any event involving Y alone, and vice versa, then X and Y are independent random variables. So probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. You should always ask whether the assumption of independence seems reasonable. And in our investigation, it is reasonable to assume that X and Y are independent since the siblings operate their tours in different parts of the country. Okay, if you're not in the same country, one's not going to affect the other. They're not competing competition. So if we actually write out our total means, here are all the possibilities listed out. And here's our probability distribution histogram. So recall we had already found the total mean as 6.85. If we sum up and find the standard deviation, actually this would be variance since it's squared, right? We get 2.0775. Again, if we wanted to find the standard deviation, we could take the square root of that. So your standard deviation of X is going to be, if we just do the X, our Pete's tour would be 1.1875. If we just find the variance, actually variance of Y, which would be Aaron's tour, that would be 0.89. So what do you notice about the variance of T? So how does our variance of X and our variance of Y compare to our total variance? Notice we can add them up. 1.1875 plus 0.89 will get us 2.0775. So as the preceding example illustrates, when we add two independent variables, their variances add. Standard deviations do not add. Okay, so again, standard deviation is when we take the square root. So on this previous example, because it was squared, that is variance. So for any two independent variables, we need to find the total of X and Y. The variances directly add. So sigma squared total equals sigma squared X plus sigma squared Y. In general, the variance of the sum of the individual independent random variables is the sum of their variances. And you can never add standard deviations, okay? So never ever directly add standard deviations. We always think Pythagorean theorem. So we can perform a similar investigation to determine what happens when we define a random variable as the difference of two random variables. So in summary, we find the following. If d equals x minus y, then the expected value of d is we can directly subtract mu sub x minus mu sub y, your average x minus your average y. General, the mean of the difference of several random variables is the difference of their means. And of course, the order of subtraction is very, very important. For any two independent random variables, x and y, for their variances, we always add. So never subtract variance or standard deviation. So in general, the variance of two independent variables is the sum of their differences. And that concludes our notes part 1 on random variables.